Okay, so let's get into a discussion of chemical bonding. That's what chapter 9 is all about. So here we're going to look at how elements combine to form compounds, molecules, and ionic compounds, and so on. So let's do a bit of a preview. So what do we mean by this term chemical bonds? Well, these are basically forces that hold atoms and ions together so that they remain stable. And these forces are, for the most part, electrostatic. All right. Which means basically that these are forces that occur between species that have opposite charges. So ionic bonding and covalent bonding are all fundamentally electrostatic forces. So just to give you some introductory ideas to what we're talking about here, consider the hydrogen molecule, which is represented by this diagram down here. Each hydrogen atom that makes up a H2 molecule has a proton at the nucleus and the electron surrounding it. So when we have the formation of the hydrogen molecule, there are a couple of forces that are involved in this molecule, in this structure. You have the repulsive forces and you have the attractive forces. Now, the attractive forces, let me deal with that firstly, um, occurs between opposite charges. So as you can see here, you have an attractive force between this proton and this electron and this proton and this electron, and so on, right? So those are the attractive forces. And then you have the repulsive forces, which occur between particles of like charges. So all the forces that exist between the protons as shown here and the electrons as shown here, those are repulsive forces. So you have these two types of forces which oppose each other. And basically when the molecule is stable, such as the hydrogen molecule, what you'll find is that the attractive forces are greater than the repulsive forces, all right? In the case of the H2 plus, where one electron is lost from the hydrogen molecule, you have some changes. And what you'll find in this particular case is that this structure is not stable, right? So you will not find the H2 plus ion existing in nature, for example. Instead, it will basically be unstable. And the reason for that at the microscopic level is that the repulsive forces in this structure will be greater than the attractive forces. All right. Now, just to show you the type of energy changes that occur as you change the distance between the two atoms in the hydrogen molecule. Let's start off with from this end right here. So this is an extreme where, well, not really an extreme, but this is a situation where the hydrogen atoms are pulled far apart from each other. So therefore, you won't have any attractive forces between the nucleus of one hydrogen atom and the electrons of the other, right? So therefore, there's very little attraction that exists between those two particles. But as they come together more closely, the attraction increases because you have the electrons from one atom coming closer to the nucleus of the other atom, all right? Until you get to a stable situation where the molecule is at energy minimum. And what was found experimentally is that the distance between the two nuclei at this point is 74 picometers, all right? And then if you try to press those two atoms closer to each other, then what you'll have now is repulsive forces taking place, right? And of course, the repulsive forces will be between the two nuclei. And as you continue to push them closer, you'll notice that this part of the graph here goes up. That basically means that the energy of the molecule increases. And therefore, it becomes less and less stable. So what we have described here is basically true for all bonds, pretty much, all right? You have repulsive forces, which tend to increase as you push the atoms closer to each other. You have attractive forces, which tend to increase up to a point as you pull the atoms apart from each other. And then after you get beyond that point, then basically there's no force of attraction or repulsion between the two atoms. Okay, so let's talk about the Lewis theory of chemical bonding. Basically, the basis of this theory is that it is the valence electrons that play the most fundamental role in chemical bonding, both ionic and covalent bonding. So what we're going to look at now is focus on ionic bonding. Later on, we'll spend some more time discussing covalent bonding because that is a bit more complex. So, ionic bonding takes place between metals and nonmetals for the most part. There are some exceptions, but generally speaking, it's the result of a reaction between a metal and nonmetal. And what you'll find in this situation is that the electrons are usually transferred from the metal to the nonmetallic atoms, and therefore ionic bonds will take place. As a result of this transfer of electrons, you're going to end up with ions being formed, and the ions will have an attractive force between them, and that attractive force will be the ionic bond, right? Then we have covalent bonding, which we'll talk about later on. Now, covalent bonding occurs only between nonmetals, and this happens by way of sharing electrons between um, two atoms. And when we're saying sharing electrons, we're talking specifically about sharing their valence electrons. So, in any compound formation from elements, you have the loss, gain, or sharing of electrons to form your chemical bonds. And in all these cases, or I should say in most of these cases, the atoms tend to acquire electrons um, or gain electrons in order to end up with the electronic configuration of a noble gas element. Um, this is not true in all cases, as we're going to see later on. There's some cases where it is simply not going to happen. But for, I would say, elements in the A group region that we talked about previously, the main group elements, they tend to behave that way more often than not, all right? So, Lewis symbols, right? This is a representation, very convenient representation of an atom indicating only the valence electrons, all right? So basically, it's a very simple process. We use a symbol for the element, and then we place dots around them representing the valence electrons, all right? It says here that in writing Lewis symbols, the first four dots are placed singly on each of the four sides of the chemical symbol. I would say that that is not always the case. I have seen in textbooks where they don't really care where the dots are as long as you indicate the dots around the element symbol, all right? Then it says dots are paired as the next four are added. Again, that is not always the case. I've seen in textbooks where they don't really concern themselves with pairing the dots. But, you can stick to this if you want to, but it's not absolutely necessary. And then it says the Lewis symbols are used primarily for those elements that acquire the noble gas configurations when they form bonds, as we said before. So just to give you some examples of Lewis symbols, we have these elements in period 2, starting with lithium in group 1A to neon in group 8A, and you'll see that basically the Lewis symbols consist of the symbol of the element and then the dots representing the valence electrons. So as you can see here, lithium has one dot, which means that it has one valence electrons. Beryllium has two, and so on and so forth for the others. Okay, so if you're given a question like this, give the Lewis symbols for magnesium, silicon, and phosphorus. That's very easy. All you have to do is consult the periodic table and look at which group they're located in. So in the case of magnesium, if you look at the periodic table, you'll see that magnesium is in group 2. So therefore, the Lewis symbol for magnesium would be Mg, and then you put one dot here, and that's that. In the case of silicon, it's in group 4. So you put the symbol for silicon, and then you just put 4 dots surrounding it like that. And then in the case of phosphorus, which is in group 5, you put 5 dots around it like that. And that would be the Lewis symbol of phosphorus. So it's a very simple representation for an atom, which only indicates the valence electrons. That's all you need to know, especially when it comes to bond formation. Okay, so let's look at ionic bonds. And then later on, as I said before, we'll be focused on covalent bonds. Now, as we said before, in the case of ionic bonding, we have atoms losing or gaining electrons. And as a result, especially for the representative elements, they will acquire the noble gas configuration. But the key thing you need to remember is that they themselves do not become noble gases. Because remember, even though they end up with a noble gas configuration, the atomic number remains the same for that element, so therefore they do not magically translate into noble gas elements, all right? Now, because the two ions that are formed have opposite charges, there will be a very strong attractive force that exists between them, and they will form what we call an ion pair. And that attractive force that I just referred to, that is what we call the ionic bonding. All right. And because that force is very strong, they impart certain properties to ionic compounds. All right. They tend to be in a solid state. They tend to have high melting points, high boiling points, and they do not conduct electricity because the ions are in fixed, rigid positions. However, when melted, they will conduct electricity, and so on. So, just to illustrate what happens in the formation of an ionic compound, we're going to use the example of sodium chloride. Now, if you have a vessel such as the one that you see here, filled with chlorine, and you drop a small piece of sodium chloride, I'm sorry, of sodium metal in it, then you're going to have a very exothermic reaction. A lot of heat and light will be generated. And that's because the sodium will react with the chlorine to form sodium chloride. So this reaction will take some time to cool down in terms of the heat generated. And then when everything cools down and you look inside it, you're going to see crystals of sodium chloride formed, right? And of course, that happens because the metal, sodium, will be giving up its electrons to the chlorine atoms of the chlorine molecule, as you can see in this diagram here. Let me go back to my pointer function here. Right, so as you can see, the sodium atoms will give their electrons to the chlorine atoms. Remember, chlorine exists as a diatomic molecule. So basically, you're going to have 2Cl atoms per molecule. So when the chlorine atoms give their individual electrons to the chlorine atoms of the molecule, the bond here between the chlorine atoms breaks up or splits up, and you end up with your sodium chloride compound. Now, one thing you need to know about ionic compounds, and sodium chloride, of course, would be an ionic compound, is that there are no discrete units of NaCl existing in this compound, right? Basically, as you can see here, the structure of the sodium chloride compound is a highly ordered structure, as you can see here, right? In fact, if you look at this closely, you'll see that you can identify what we call a unit cell, which contains a certain number of each ion and the way they're ordered. And that unit cell repeats right throughout the whole system. So if you look at the gross structure of sodium chloride, you see the repeat unit cell going in basically the three-dimensional direction, X, Y, and Z direction, all right? So that's basically characteristic of all ionic compounds. I would say the only difference between them is the arrangement of each unit cell. But once you establish what the unit cell is, you'll notice that it repeats right throughout the structure. Okay, how do we show ionic bond formation using Lewis symbols? Well, Lewis symbols can be used to represent ionic bonding between nonmetals and S block elements, some P block elements, and very few D block elements, all right? And basically, instead of using the complete electron configuration, we can simply use the more fundamental or simplified Lewis symbol, as you can see here in this example. So if you look at this example, you'll see that you have chlorine. This is the Lewis symbol for chlorine, and sodium, right? As you can see, sodium has 1 electron. Chlorine has 7 electrons on its valence shell. So what will happen in this case is that the sodium ion will give up its 1 electron to the chlorine atom, and now the sodium ion has basically a Lewis structure, which would be the same as neon. So the configuration of the sodium ion would be the same as the electron configuration of neon. The chloride ion, on the other hand, as you can see now, has a full octet of electrons. And if you look at it closely, you'll see that the chloride ion has the same electron configuration as argon. So in this particular case, you'll see that the electron configuration of the ions formed is the same as the electron configuration of the nearest group 8 elements, respectively, for each of these elements indicated. Okay, so based on what we have just learned, you should be able to do this example. Let me go back to my pen function here. And this question says, use Lewis symbols to show the formation of the ionic bonds between magnesium and nitrogen. What are the name of and the formula of the compound that results? So In the case of magnesium and nitrogen, magnesium has 2 electrons on its outer shell, and nitrogen has 3 electrons on its outer shell. Actually, 5 electrons. I'm sorry. So 5 electrons on its outer shell, right? So in the case of magnesium, it needs to lose these 2 electrons, but in the case of nitrogen, it needs to gain how many electrons? 3 electrons, right? In order to obtain an octet. So how is this accomplished? Well, it's accomplished this way. The magnesium, I would just multiply this by 3, and I would multiply this by 2. So if I were to write out the 3 magnesium atoms separately, it would be like this. And in the case of the 2 nitrogen atoms, and here, okay. So what will happen, let me go to my eraser function because I need to make this more clear. I need to erase this right here. Okay, so, come on. Ah, okay, I don't know. Okay, now I got this right. Okay, so what's going to happen here is that you'll have the transfer of electrons. So I'll start off with this magnesium here. I would transfer 1 electron to here. I would transfer this electron to here. And then I'll transfer this electron to here. And then this electron will go here. And then this electron will go here. And finally, this electron will go here. So the result of that will be you're going to have 3 magnesium ions and 2 nitride ions. And each nitride ion will have 8 electrons, an octet, on its valence shell. So that's why the formula for magnesium nitride ends up being Mg3N2. All right? So that's basically how we use Lewis symbols to show the formation of an ionic compound, in this case, magnesium nitride. Okay, I'm going to stop here for now, and then the next thing we're going to discuss is how we can determine what we call the lattice energy, which is a reflection of how stable an ionic compound is. Okay, so until next time.